All right, in the last video we talked about how we can identify a DP idea in the coin change problem. And the basic idea is if I want to know optimal change for 6, I can get that really easily if someone tells me optimal change for 2, 3, and 5, right? So the DP idea when we take this to an algorithm is we say, oh, well, then we better go find optimal change for 2, 3, and 5. Okay. So one way to think about doing this, and I briefly started talking about this with the last kind of the last video. One thing that we see almost immediately, and we'll be very explicit about this with a recursion tree in a minute. One thing we see almost immediately is that we need to know almost all the change amounts, right? To find optimal change for 6, I need to know 5, 3, and 2. I can't get away with skipping any of those 3. Okay. So that means, and then to find optimal change for 5, I have to know 4, 2, and 1. Well, I've just written down everything, right? 1, 2, 3, 4, and 5 are all now in my required information. So there's really no algorithmic way to find optimal change for 6 without also finding optimal change for 1, 2, 3, 4, and 5. So this suggests that maybe in this algorithm, we could just start at 1, find optimal change for 1, which is the trivial case, and then use the DP idea to find optimal change for 2, then use it again to find optimal change for 3, and just work our way up, saving our answers as we go until we get to 6, right? Because we know that optimal change for everything below 6 gives us the answers to optimal change for 6. So let's just build it up as we go. So here's the idea. Start at 1. And I'm going to write a couple things down. These functions, they'll look like functions. They're really kind of enumerations. They're going to be the stuff that goes in our DP table. So our DP table info. Remember, the DP table is this table of information that we store to try to save the solutions to subproblems as we go. So I'll say n of I is the optimal number, or I should write minimum because, let's be precise. Minimum number of coins to make change for I, and I'm way into the picture there. So n of I, if I plug in 5, that'll tell me 2 or whatever it is, the minimum number of coins it takes to make change for 5. Okay, and then C of I is going to be a set, and this is going to be the optimal set of change. Optimal change for optimal change for I. Okay, so the goal of the problem is to find n of little n and c of little n. Right, so the algorithm's goal find n of little n, right, the number of coins it takes to make change for little n, and c of n. And I guess really all we need is c of n, right, because c of n tells us the set of coins, the optimal set of coins to make change for n. So let's now build up our DP table, okay, using information that we have. So what I'm going to do is I'll write I as one column. I'll write n of I as another column. And I'll write c of I as a third column, okay? So this will be my DP table. And I'll fill in rows here, and then as I fill in the rows, I'll also write some math on the, I'll slide over here and I'll write some math that describes what's going on. So if I is 0, then by definition, right, I'm asking what's optimal change for 0. The answer is there's no change. There's no money, right? So it doesn't take any coins to do that. So the optimal number of coins is 0, and the optimal set of coins is the empty set, right? Nothing interesting has happened here. Okay. So now I can say what is n of, I'm going to space this out a little bit better. What is n of 1? Right? If I say what's optimal change for 1, what is this? Well, I can be very, very pedantic about this and say, look, optimal change for 1 can be expressed as, and let me write this actually as a fourth column. So here's the mathematical expression. So optimal change for 1 goes like this. It's n of 1 equals, there's always going to be a coin, right? There's some coin in there. And that coin is going to be added to the optimal change for whatever is left when I remove that coin. Okay, so this is added to optimal change, n, right? So this is an expression for optimal change of the amount of 1 minus whatever denomination fits. There's only one denomination that fits here, so you know this is just d1, which is 1. So this is equal to 1 plus n of 0, which is 1. And so now if I zoom out just a bit, you can see that the final expression here is stated in terms of stuff that I know. I already know n of 0, right? So n of 0 plus 1 is just 1, and we're done. So what does that mean? N of 1 is, n of 1 is 1, and what coin is used for this? D1. And how do I know D1 is used for this? Because it showed up here. Okay. We'll see more complicated examples in just a moment. Right? But this one is still almost trivial. But for the sake of algorithmic completeness, we want to make sure that we understand these simple trivial cases because they're going to be executed by the algorithm. Right? They don't, just because it's trivial doesn't mean we get to ignore it. All right, so that's how I equals 1 works. Now let's think about I equals 2. So what is n2? Well, let's go think about it with the math. So n of 2 is always, it's 1, right? There's a coin in it. So now let's remove that coin. What coin could it have been? Well, there's only one coin that fits into 2, right? And that's the 1 cent coin. We know that a 3 cent coin doesn't fit. We know that a 4 cent coin doesn't fit. So the only coin that could fit into 2 is the 1 cent coin. So we're basically just going to copy the same expression from above. So this is going to be n of 2 minus d1. So d1 is 1. Right? So let's just make sure that stuff's clear. d1 is 1, d2 is 3, d3 is 4. Those are our 3 denominations. So d1 is 1, and so this is equal to 1 plus n of 1. Now we know n of 1, right? N of 1 we calculated before. N of 1 is here. So all we have to do is plug that in, and we're good to go. So here we plug that in, and we get 2. Now this one, again, this is bordering on trivial. Because there's only one denomination that even matters, and you know there's nothing surprising about the fact that it takes 2 pennies to make optimal change for 1. But this is all legwork that we have to make sure we go through. I'm going to change this actually to a tuple because it doesn't make sense to make it a set. And so how many coins does it take to make change for 2? Well, it takes 2. And those coins are a D1 and a D1. Okay. All right. And how did I know it was D1 and D1? Well, let me be very explicit. This is equal to D1 plus D1. Right? Being a little bit flaky with my math here, and where did that second D1 come from? It came from here. Right? The fact that I used it in my mathematical expression, that I used a 1 cent coin to get me down to something that I know, means that it gets added to my optimal change. Okay, so now let's go to our first interesting one. So our first interesting one is when I equals 3. So what is n of 3 then? Well, n of 3 always is going to be 1 plus something, right? 1 plus n of something. But now there's a couple different options, right? So now there are 2 different coins that fit into 3. So it's either going to be the minimum of 3 minus the first denomination, or it's going to be the minimum of 3, or it's going to be 3 minus the second denomination. Okay, so here is the full expression. So it's going to be the minimum of 2 different possibilities. One is 3 minus d1, and the other is 3 minus d2. Minus d2. Okay, why? Because those are the only denominations that we can subtract off of 3 and get a positive number. Okay. So which one of these gives us a smaller number? Here, well, I need to actually scoot this over a bit. My minimum needs to go inside, or my n needs to go inside here. There we go. Couldn't do that on a whiteboard. All right, so there's n of... Okay, so what we need to do now is figure out what those two numbers are, right? So n of 3 minus d1, what does that mean? Well, that means the optimal amount of change to make change for what we get if we take a penny out of optimal change for 3. Okay, this is, I know that's a mouthful, but it's, you know, n of these n of different numbers are stuff that we have, right? We've been recording n of a bunch of numbers as we go. So let's go figure out what n of those numbers are. So we're going to fill out, we're going to write everything in here. So this is equal to 1 plus the minimum of two numbers, right, of n of one thing and n of another thing. So 3 minus d1, d1 is 1, so this is 2. So this is n of 2. And the second number here, 3 minus d2, well, remember d2 is 3, so 3 minus 3 is 0. Okay, so what this tells us is either the optimal change for 3, right? Remember, this whole line of math is we're trying to identify the number of coins in the optimal change for 3. So the optimal change for 3 either contains optimal change for 2, or it contains optimal change for 0, right? If it contains optimal change for 2, then it also contains a penny, contains a d1 equals 1. If it doesn't contain optimal change for 1, then it contains a d2 equals 3, a 3-cent coin. Okay, and so, you know, n2 is 2, n0. So here's n0, here's n2. It's clear which one is smaller, right? The 0 is smaller, and so this equals 1 plus the minimum of 2 and 0, which equals 1, right? And so what does this 1 represent? Well, this represents the number of coins in optimal change for 3. Okay, so now we know that it takes only 1 coin to make optimal change for 3, and that's not surprising because one of our denominations is 3. Okay, so now we know optimal change for 3, and we can also identify what set of coins gives us that by noticing that this right here, this argument of the minimum, is the one that gave it to us, which is this, which we said means that the optimal change contains a D3, okay, and nothing else, right? A D3 and then whatever optimal change was for 0, right? So this is just then, or sorry, not a D3, a D2. Yep, got it, D2. Okay, so there we go. Now we've identified everything up to optimal change for 3. Okay, so now I'm going to go ahead and fill the rest of this table out. I'll move a little bit more quickly as I do it, because I hope people are getting the idea, or at least can back up a little bit and review the idea to make sure that it comes out clear. This algorithm is also in the book, presented a little bit differently, I think. But let's proceed. So to find the number of coins for optimal change for 4, I've got n of 4 equals 1 plus the minimum of now 3 different numbers. So minimum of n of 4 minus d1, n of 4 minus d2, and n of 4 minus d3. 4 minus d3. Okay, and so now I can zoom out a bit to make some space here. This is equal to 1 plus the minimum of n of 3, n of 4 minus d2, so d2 is 3, so that's 1, and n of 0. Okay. So now I can focus just on this one, and I can say these numbers are all things that we know, right? We can read these out of our DP table. We just figured out that n of 3 is 1. We knew for a while that n of 1 is 1, and n of 0 is 0. So this is min, or sorry, it's 1 plus min of 1, 1, and 0. Right, and the smallest of those three is 0, or is 0. So that means we have 1 plus 0, so this is 1. Right, so what does this one represent? That represents D3, right? That represents a 4-cent coin was used. This one represents D2, a 3-cent coin. And this one represents D1, a 1-cent coin. And so because the one that gave us the smallest amount was a 4-cent coin, now we know two things. We know that optimal change for 4 contains a 4-cent coin, as well as optimal change for 0, which is, of course, 0 coins, and that the number of coins in it is 1. Okay, so now we can fill in those spots of our DP table. So 1, and then this is D3. Okay. So now to do 5, or not, sorry, I should better not write a 1 where it isn't a 1. So what is n of 5? Well, it contains a coin. Now let's think about what would the ramifications of various identities of that coin be. So that says min n of 5 minus d1, n of 5 minus d2, n of 5 minus d3. So this is 1 plus the minimum of n of 4, n of 2, n of 1. Okay, we know these numbers. These are all numbers that show up in our table. So this is 1 plus the minimum of 1, right? Because it takes 1 coin to make change for 4. 2 makes 2 coins to make change for 2, and 1 because it makes 1 coin to make change for 1 So which is the smallest? Well, now there's 2 minima here, right? Or there's 2 minimizers. Sorry, 2 minimizers. Only 1 minimum. The minimum is 1. But there's 2 minimizers, and those correspond to adding a 1-cent coin and to adding a 4-cent coin. And so it doesn't really matter which one we pick, right? The answer is going to be the same. It takes 2 coins. One of them is a 1-cent coin, and one of them is a 4-cent coin. And so this is equal to 2. Oops, let me switch back to black. This is equal to 2. And either we say, hey, it's a 1-cent coin plus however many coins, whichever coins it takes to make optimal change for 4, or we say, hey, it's a 4-cent coin plus however many coins it takes to make optimal change for 1. In either case, it's we get a 4 and a 1 as our optimal change. Okay, so here we end up with 2 coins, and the denominations are D1 and D3. Okay, and then finally at the very end, here we have a 6. We want to figure out what is n of 6. It's always going to be 1 plus the minimum of several numbers. So this is n of 6 minus d1, n of 6 minus d2, n of 6 minus d3. So this is n of 1 plus the minimum of n of 5, n of 3, n of 2. And right, so now we can plug numbers in. Those n's are all from our DP table. So this is 1 plus the minimum of n of 5 is 2, n of 3 is 1, and n of 2 is 2. And so now we have a unique minimizer, right? And so this, if we just want to keep track of what's what, this is D3. This is a 4-cent coin. This is a 3-cent coin. This corresponds to a 1-cent coin. And the minimum is 1. The minimizer is the minimizer here is the 2-cent coin. And so in the end, we just do the math, and we have this coin plus that coin gives us 2 coins. And because it was the 3-cent coin that gave it to us. What we're saying we're going to do is we're going to append a 3-cent coin to optimal change for 3. So append a D2 equals 3 coin to optimal change for 3. And so in the end, what we get is this takes 2 coins, and the coins are D2 and D2. Okay. And so that is a very, I mean, it's an extremely detailed, absolutely step-by-step description of the DP algorithm for change making. And this is called a bottom-up DP change algorithm, or DP algorithm. And here what bottom-up means is that we're starting at 1 and we're working our way up and solving all of the subproblems, starting at the smallest, working all the way up. So we're not leaving any of the subproblems out. There aren't any change amounts that we're ignoring here. We're just going to go solve them all. Next time we're going to find some applications where sometimes we can think of going top down and be really smart about exactly which subproblems we solve. In this one, the smartness just comes in being sure that we're not solving any subproblem twice. So we never say, you know, what is optimal change for 4, and then later on ask what is optimal change for 4, and don't look up our old solution. Right? We always save the solutions to the things that we've solved. So in the next video, I'm going to give you a pseudocode explanation of this algorithm, and then we'll wrap it up.